This is your lesson for 6-4 logarithmic functions. There is an explore and reason in your textbook. That's on page 321. You may or may not be completing that depending on other instructions for the course. So our essential question for 6-4 is, how is the relationship between logarithmic and exponential functions revealed in the key features of their graphs? So this section is mainly going to look at graphing logarithmic functions and then looking at the relationship between how logarithmic and exponential functions are inverses of each other. We're going to use that idea of inverse to graph the logarithmic function. So our example here, it says graph y equals log base 2 of x. What are the domain, range, x-intercept, and asymptote? And then what is the end behavior of the graph? So the inverse of log base 2 of x, if we look at the inverse of that, the inverse is y equals 2 to the x power. So normally, if you were to rewrite this log base 2 of x equals y, you would get 2 to the y equals x, and then remember, we reverse our x and y's to do the inverse. So if I look at the table here of the inverse, if I use the values -2, -1, 0, 1, and 2, at -2 I get 0.25, at -1 I get 0.5, 0 is 1, 1 is 2, 2 is 4, and so on. So now if I look at my log, because that's the inverse, the table for that is going to be all of those points reversed. So I have 0.25 and -2, I have 0.5 and -1, I have 1 and 0, I have 2 and 1, and I have 4 and 2. So that graph is going to look like this. So 0.5 is at -1, at 1 I'm at 0, at 2 I'm up at 1, and then up at 4 I'm out at 2. So that is going to look like this. Whereas the exponential function is going to look like that. So there's the exponential. The logarithm is the one in green. That's the one we're looking at. That's the one where we're going to name the domain and range. So with the original exponential in blue, the domain was all real numbers. Well, since logarithm is the inverse of that, your range is going to be all real numbers. Notice my y's are getting smaller. They're also getting bigger. They're going to keep going down to the negatives, keep going up to the positives. However, for the blue one, my range was 0 to infinity, and that is actually going to be the domain. Remember, you can't plug in a negative number. You can't take a logarithm of a negative. You also can't take a logarithm of 0. So that's why our domain ends up being 0 to infinity. My x-intercept, well, there was no x-intercept for the blue function, but it did have a y-intercept. And so that y-intercept of the exponential actually becomes the x-intercept of the green logarithmic function. And so that x-intercept is going to be 1. And our asymptote, remember, exponential functions have a horizontal asymptote. Your logarithmic functions are going to have a vertical asymptote. So my asymptote here is going to be the line x equals 0. Again, it's the inverse of what we had for the blue exponential function. The last thing we need to do is the end behavior. You kind of have to be careful with this one because I can't say as x approaches negative infinity because it's not possible for the x to reach negative infinity. So I would have to say as x approaches 0, then f of x is approaching negative infinity. So this is reversed because before we would say for the blue one, as x approaches negative infinity, f of x approaches 0. Again, this one is swapped. And then as x approaches positive infinity, f of x is approaching positive infinity as well. So that one, you do reverse it there too, but it ends up being the same thing. There is a way to graph logarithmic functions on your calculator, and that's something you may see in a later course. This isn't going to be a huge thing. I just wanted to make sure we really address the fact that logarithm is the inverse of the exponential. Next one, graph the function. How did the asymptote and x-intercept of the given function compare to those of the parent function? So the parent function, f, that's what we just graphed in the previous question. That's log base 2 of x. So if you recall, I had the point 1, 0, 2, 1, 4, 2. Half was down at -1, and then I was down at -2. So there's my parent function. This one has that +3. So this is the movement just like we had before. Remember, we had the h and the k. So this is actually moving my graph to the left 3. So I'm going to take all my points, 2, 3, 2, 3, 2, 3, 1, 2, 3. So everything is going to move that way. So everything is moving to the left 3. This is an h and k relationship, just like we had with a lot of other things that we've worked with. So the asymptote is going to move left 3 units. So that's going to become x equals 3. And the x-intercept also moves left 3. So we have this relationship. I'm going to write this down here in red. If you have your function, you have your log of your base. I'm just going to call it 2 in this case. But remember, it's x minus h and then plus k. So if there's a plus on the end of it, that's going to move your graph up. If there's a negative on the end or a minus, it's going to move down. H is opposite. H tells you left to right movement. So you can put numbers in front. So I could say, okay, there's an a in front of that. That's going to be your dilation factor. So it's going to be a multiple. And then your base could change. This is a base 2, but it could be base 3, base 4, base 5, whatever base you needed. Next, what is the equation? The inverse of the function. So this is where we are going to swap the x and the y's and then resolve, and that will give us our inverse. So the first thing you need to do is change the f of x in your problem to a y, or the g of x, or whatever function notation they give you. Now that it is in a format where it has the letters x and y, we are going to swap x and y. So I have x equals 10 to the y plus 1 power. And then I have to go through and get the y by itself to get the actual inverse equation. To do this, I want to rewrite this as a logarithm. My base is going to be 10. So since that's a base 10, I don't have to write logarithm base 10. So I'm taking the log of x, and that's equal to y plus 1. Then to get the y by itself, I would subtract 1. So this is log x, and then minus 1 is equal to y. So that means my inverse, and again, my notation with the -1 there, that means inverse. So I'm basically taking that y and turning it back into function notation. This is log x minus 1. So again, the inverse of the exponential, 10 to a power, is a logarithmic function. And we're going to do the same thing with part B. So I'm going to take my g of x and turn it into a y. So this is log base 7 of x plus 5. So now to do my inverse, I'm going to say x is equal to log base 7 of y plus 5. So this one isn't a logarithm. I'm going to rewrite this as an exponential. So this is going to be 7 to the x power is equal to y plus 5. You're doing the swirl, but you're kind of going the opposite way because I have the equals on the other side. And then we get 7 to the x minus 5 is equal to y. Again, we go back here and put it back into our notation. So our inverse is equal to 7 to the x power subtract 5. And if you were to graph these, you would see that they would fulfill all the requirements needed to be inverse functions. Next, we have a word problem. So this is an equation. It says company uses this function to relate sales revenue R and advertising costs A. So R is in thousands and A is also in thousands of dollars. So we have R equals 12 times log of A plus 1 and then plus 25. We want to know what's the equation, the inverse of the formula, and which equation would be easier to use to find a value for a particular, find a value of A for a particular value of R. So to find the inverse equation, we are actually going to go through and solve for A. So the equation of the inverse of the formula, that's where you get the A by itself. So we're going to go through and solve this. So let me recopy this. I want to subtract the 25 first, because I do need to get this logarithm by itself. So I'm going to subtract the 25, and I'm also going to divide by 12. So I'm just going to go ahead and do both of those things now so that I have them. Now I'm going to change this from a logarithm to an exponential. My base here is 10 because this is a common log. I don't see that base. So 10 to the R minus 25 over 12 power is equal to A plus 1. So R minus 25 over 12 power is equal to A plus 1. And then you would subtract 1. So 10 to the R minus 25 power over 12 minus 1 is equal to A. That is going to be the formula of my inverse. So that is my equation where you're able to solve for A if you know the R. And that answers your last question, the last question of this problem. Which equation would be easier to use to find the value of A for a particular value of R? It's going to be a whole lot easier to find your A value when an R is known if you use the A equals equation than if you were just using the original R equation. And I don't necessarily agree with the fact that this is an inverse. Although I guess if you swap the A and the R and you resolved for the R, you would probably get the same thing. This is really just writing the equation in a different format. So this is your inverse equation, however. Lastly, comparing to logarithmic functions. So we can use these to approximate altitude of a plane because you can see when a plane takes off, they rise very quickly and then they kind of plateau, although they are still rising a little bit. And that's why this T is using the time frame that it is, because the further out that you get, once your plane reaches its ideal altitude, they're not going to keep climbing. So that's one reason why this equation is only good for probably maybe 20 or 30 minutes after takeoff. So we have plane A, which has an altitude that's approximated by A equals 9,200 times the natural log of T, and then plus 10,000, where T is time in minutes after takeoff. And then A is going to be your altitude in feet. So the second one then gives us a graph. They don't give us the equation here, but they do give us 2 points in time, the 10 minutes and the 15 minutes, which is what we need for this question. So for plane A, because we want to know which one has the greatest rate of change. So this is going to be f of 15 minus f of 10 all over 15 minus 10. And that's going to be for both of those. And I guess instead of f, I really should use A. So I'm going to change that so my variables match what I have in the problem here. So you would take the 15 and plug it into this equation with the natural log. So for plane A, when we plug in the first one, I get 34,914. If I plug in 10 to the first equation, I get 31,184. And then I'm dividing that by 5, and we get 746 feet per minute. So the rate of change of their altitude is going to be 746 feet per minute for plane A. For plane B, I can use my numbers that I have here. So A of 15 is my 39,449. A of 10 is the 37,497. And then when I divide that by 5, I get 390 feet per minute, which means plane A, it says which one has the greater rate of change over the interval. That is going to be plane A because its rate of change is actually almost double what it is for B. In your textbook on page 324 is your concept summary. This goes over, again, reiterating the relationship between the logarithmic functions and the exponentials and how logarithms are inverses of the exponentials, why they're necessary, and how you can tell different things about the graphs based on that relationship. So go back through, review this lesson, and reach out to me if you have any questions at all on logarithmic functions.